Jake, thanks for the.
Of course, I'm happy to just talk to you.
Yeah,
I want to
no.
put it in writing just in case.
That's your student that I talked to in your
Oh, yeah.
patio, right?
Yeah. It's not good.
Yeah, he just arrived, yeah. So I really hope people will speak up and interrupt and
questions.
ask questions,
Yeah.
and you can, you know,
I'll ask some stupid questions.
that's fine. That's
Yeah.
fine. You can ask what in at Princeton we used to call the Hungarian question when Eugene Wigner would raise his hand and say, I think I probably told you this story. Some guy wrote down the equivalent of 2 = 5 on the board, and then they're very polite. Excuse me. I don't understand your notation. What do those 2 parallel lines mean? They didn't want to say you're wrong. Just
Certainly friendly on that.
yeah.
What's that?
Yep.
Hey, guys. We have the pleasure of giving Steve Girvin tell us about the circuit QED existing from Yale University.
Thank you, Matthew. It's a pleasure to be here. I have 4 lectures there. Thus, all the slides are posted on the website, and under lectures and under reading material, there's a big set of lecture notes on this topic from the Les Houches Summer School, and also an appendix to show you how to calculate the S matrix for microwaves bouncing off a cavity containing a qubit, which I'll just outline in the slides. But if you want to see the derivation, it's in the reading material. Yale is very serious about us disclosing any external interests. So I'm telling you that I'm a consultant with Quantum Circuits Inc., a Yale startup, and I own a few shares of IBM, which is partly a quantum computing company. Okay, so circuit QED is next year will be the 20th anniversary of the first papers, and it brings the ideas of cavity QED and quantum optics to superconducting microwave electrical circuits. And lasers are replaced by microwave signal generators, and natural atoms are replaced by synthetic atoms, superconducting qubits. So this is going to be, the physics here is going to be kind of quantum optics, but the applications will be quantum sensing and quantum computing and quantum simulation and quantum error correction. Okay. Good. So these Les Houches lectures are available on my website and also posted on the school's website. If you're interested in quantum error correction and fault tolerance, here's another reference. Okay. So I hope that my goal is maybe to not even finish all 4 lectures, but to have so many interruptions and questions that I managed to uncover a little rather than cover a lot. So there's nothing worse than getting lost and not raising your hand and then not being able to follow. So please don't be shy. Ask me questions. So I'll start with what is cavity QED, cavity quantum electrodynamics, from which these circuit QED ideas are descended. Then I'll show you how to quantize the only thing I understand, the harmonic oscillator, but the electrical version rather than the mechanical version. Then I'll explain how Josephson junctions work and Transmon qubits work. And then I'll show you how to couple those to microwave cavities and use the qubit to read out the state of the cavity and the cavity to read out the state of the qubit. Okay. All right, so what's quantum electrodynamics? It's the study of photons coupled to charged particles, typically electrons, because they're the lightest and most readily accelerate when you apply an electric field to them, unlike the nuclei. In particular, quantization of the electromagnetic field introduces new phenomena. When you studied the hydrogen atom, you found out there were energy eigenstates, right? And Rydberg series and so forth. Well, it turns out those are not energy eigenstates when you quantize the electromagnetic field, because the vacuum fluctuations cause empty space to be full of electric fields. They're bigger than you think, actually. And they destabilize, let's say, the 2p orbit of hydrogen and cause the electron to fall down to the ground state, and the atom spontaneously emit an ultraviolet photon with an energy of 3/4 of a Rydberg in about 1 nanosecond. Okay, so it's actually not very stable. It also does some other things, like the electron can virtually emit and then reabsorb a photon, giving it a kind of self-energy in many-body language. And that the processes for doing that are slightly different because of matrix elements differences and selection rules in the 2s and 2p states. So they're split apart by a tiny amount called the Lamb shift. And the prediction and correct measurement of that and calculating it so that it wasn't equal to infinity and getting the right answer were early triumphs after World War II of quantum electrodynamics. So those are 3 examples of things that vacuum fluctuations do to natural atoms. The goal of cavity QED and circuit QED is to modify those things by modifying, filtering, changing the spectrum of vacuum fluctations that the atom sees. So as quantum electrical engineers, we're going to think of this as filtering. As an optical person, you can put highly reflecting mirrors and trap photons between them. And instead of having a continuum of photon states, you get a discrete set of, fundamental, first harmonic, second, and so forth. Typically, these are millimeters to 10 centimeters apart. So there's a huge number of modes. And also, when the atom falls in there, it does talk in a special way to those modes that have frequency near the atom transition frequency and are trapped by the cavity. But typically, the cavity is very open. And if the atom is in the excited state, it still can mostly spontaneously emit photons out the sides at the same rate as in the vacuum. So in optics, they don't typically look at the spontaneous emission is not strongly affected by the cavity. But in the microwave world that I'm going to be talking about, so our synthetic atoms spontaneously emit in the gigahertz frequency range, microwave centimeter scale wavelengths. we can surround the atom by mirrors that on all four sides. So it's just a superconducting aluminum box machined in the machine shop. And you get 4 pi of coverage, and the thing can't radiate in any direction. And also the size of the box is not hundreds of thousands of, or tens to hundreds of thousands of wavelengths across. It's half a wavelength or 1 wavelength across. So the energy spacing of the modes is comparable to the frequency itself, very large compared to here. Okay, so I'm going to tell you about what happens to quantum electrodynamics when you discretize the spectrum of the electromagnetic field, or filter out certain components of the vacuum fluctuation. So there's no spectral density at frequencies other than the normal modes frequencies of the box. Yeah. So originally they just fell through under gravity. Then they, basically developed ways to put such strong electric fields here that they could get trapped and held in a tweezer-like fashion, even in the presence of gravity. Ours are glued down, and they're a millimeter across. We don't lose sight of them. Yeah, good question. So in the old days, they just fell through, and that was it. Saw a little blip in the. They had some minor effect on the beam transmitted. So I'm going to tell you about Transmon qubits, which are synthetic atoms with a built-in microwave antenna. So they couple as strongly as possible to the electromagnetic field at the limit set by the size of the fine structure constant. And they will, just like hydrogen, if you put it in the excited state, it will spontaneously fluoresce and emit not an ultraviolet, but a microwave photon in about 100 microseconds. The very same identical calculation that you do for here, but just different parameter range. You get about 100 microseconds. 100 nanoseconds, sorry, 100 nanoseconds. Well, that's pretty terrible. Our qubit doesn't live long. Yes? Sorry? I will explain what it's a superconducting qubit. I'll explain what that is. But by putting our synthetic atom, our superconducting qubit, inside a box that does not have any modes at the transition frequency of the atom, it cannot radiate. And the line goes up by a factor of 1,000 to 100 microseconds, or even a millisecond. And that's very good for our, building a quantum computer. Okay. Yep.
Did you say that the idea is that there are no vacuum fluctuations inside the box because it's too small?
There are vacuum fluctuations. Each mode of the electromagnetic field is a harmonic oscillator. Its position is the value of the electric field here, and the momentum is the magnetic field. And if you look at each one has some uncertainty in position and momentum. So electric and magnetic fields, those are the vacuum fluctuations. But because there's not a continuum of modes, a continuum of oscillators, the spectrum of vacuum fluctuations is discrete. That's the difference. Does that make sense? Good question. Other questions? Good. Yes.
Just a figure of merit, right? Not
We'd like it to be 1 billion. That's our engineering task. We've gotten it to 1,000, and we're still working. Yeah. It turns out that the Q of these cavities is not infinite, especially if you want to get information in and out of them. You have to open a door. But it turns out that actually the limiting factor is the junk. It's a technical term, the junk that has imaginary part of its dielectric constant in the vicinity of the atom, the synthetic atom, which I will explain later. Okay, so other people have done microwave cavity QED with what they consider gigantic atoms, Rydberg atoms with an electron in the 50th or 51st circular orbit. And they are relatively big, but still much smaller than the millimeter scale of the atoms, the synthetic atoms I'll show you. And they have a very high Q niobium microwave resonator. They prepare the atoms in state 50 or 51. Those are the two states of the qubit. And then they interact it with the microwave field, and then they measure the state of the atom. And this atom or qubit has a transition frequency about 50 gigahertz. Or you can do, as I said, optics, where you can, in the old days, it just dropped a cloud of atoms through there and it fell through. Now you can trap individual atoms or optical lattices of atoms. And you can't really, like, as I said, the fluorescence of these guys is still very fast, in 1 nanosecond, because it can emit stuff not captured by the cavity. But the presence of the atoms can perturb the light that passes through, and you measure something about the atom's presence by looking at the light rather than directly measuring the atom. Those are sort of the two pictures. Okay, so we're going to do, we'll figure out, we're going to use the ladder system where we're going to measure. We're going to bounce microwaves off of our cavity and see how it's affected by the state of the atom. We'll come back to that later. Okay, questions? All right, so quantum LC oscillators. So I don't know, when I first saw the quantization of the electromagnetic field, it was so confusing because there was position X in space, which was not the oscillator, which it had always been when I learned mechanical oscillators. And there are an infinite number of modes, and it was all very confusing. So I'm going to start with replace, because this cavity is only, let's say, a half a wavelength on a side. There is a classical mode at some frequency, and the next mode is a factor of 2 at least above that. So we can just focus on a single mode, and you could solve Maxwell's equations, figure out the Lagrangian for that mode and the Hamiltonian, and quantize it. But it's completely morally equivalent to this: an object that has a single mode and an inductor and a capacitor. And the electric field of the mode, let's say at this point, that's the coordinate, and we could use, the charge on the capacitor. The electric field lives here. The magnetic field lives inside the inductor. So the excitations of this object are photons. They're just a little weird. The electric field lives here, and the magnetic field lives over here. Okay. But if you go to the whole field theory thing, you still get this when you consider a single mode. So let's just do that. Okay. So this is called a lumped element approximation to the cavity. Lumped element approximations. You could have an actual inductor and capacitor in your circuit, and it has a certain resonance frequency. And if the wavelength of light at that frequency is much larger than the size of the object, you can approximate it as a lumped element. Okay, so we're going to deal with two quantities: the charge on the capacitor and what's called the flux. The flux is defined to be the integral over time of the voltage at this point relative to ground. This is taken to be 0. Okay. So if I differentiate, why do I call it the flux? Well, if I take its time derivative, I get the voltage across the inductor. And except for a minus sign that's always confusing, this is Faraday induction. Okay, so this is in fact the flux through the inductor, and its time rate of change induces the voltage. Okay, so it's just Faraday induction up to a minus sign. Okay, so what is the electrostatic energy? Well, I could write it as charge squared over twice the capacitance, but I'm going to write it as 1/2 the capacitance times the square of the voltage. Okay, so this is the electrostatic energy. It's like potential energy. And yet when I write it, it looks like kinetic energy of a mass equal to capacitance times the velocity squared. But it physically represents the electrostatic energy. Okay. Now, what about the magnetic energy? Well, that's 1/2 the inductance times the current squared. And because the flux is current times the inductance, I can write it as 1 over twice the inductance times the flux squared. Is that clear? So you remember the magnetic energy density, B squared over 8 pi. No, okay, B squared over 2 mu naught. We have to use SI units. This is the magnetic field squared term integrated over the volume of the inductor. Okay. All right. So now I can write down the Lagrangian. And since that looks like, I'm going to call that the kinetic energy of my oscillator, even though secretly it's the electrostatic potential energy. And I'm going to call that the potential energy of the spring. And conveniently, the inductor is shaped like a spring. So you can remember that. Okay. So I have the Lagrangian. It's just that of a harmonic oscillator. Okay. All right. So I can, all right. I'm told I have to remember to write very large over here. So somebody stop me if I start getting too small. So I'm going to slow down and just now derive the Hamiltonian. And I expect it to look like a harmonic oscillator with mass m and spring constant 1 over L. Okay. All right, so first I have to find the canonical momentum conjugate to the coordinate phi. It's kind of arbitrary which one is coordinate and which one is momentum. I've taken the flux to be the coordinate, even though it changes sign under time reversal. I had an undergraduate professor who always, when he was about to do something clever, he would say, with malice aforethought, I'm going to name the momentum conjugate to the flux with the letter Q. It's the capacitance times the voltage. So that's why I named it Q, because it's the charge on the capacitor. Okay. So charge and flux are going to be canonically conjugate and not commute. Okay. And so then I write down the Hamiltonian. And I get P squared over 2m for kinetic energy, even though secretly it's electrostatic potential energy. And I get 1/2 spring constant times coordinate squared. Okay. And I remember that the red frequency of an oscillator is square root of spring constant over mass. That's 1 over the square root of the mass, and the spring constant is 1 over L. So I get the standard formula for the resonance frequency of an LC circuit. Okay. So you can verify now from Hamilton's equations of motion. Let's see. So the rate of change of momentum is the force, which is the gradient minus the gradient of the potential energy. And that's equal to minus phi over L, which is minus the current flowing. And if you go back to up here, my sign convention, the current accelerates when the voltage is positive. So the current is going this way and through the inductor. And so the charge is decreasing when the current is positive. And that's where that minus sign came from. Is that clear? Can everybody see that over there in the corner? Okay. All right, and then the other Hamilton equation of motion is the velocity, is the derivative of the Hamiltonian with respect to the momentum, which is Q over C, but that's just the Faraday induction. Time rate of change of flux is the voltage across the inductor. Okay, and so Faraday induction, and this really represents charge conservation. If there's current flowing through the inductor, it has to be leaving the capacitor. Questions? Okay. All right, well, that's straightforward. Now I'll give the people in that corner a hard time by writing over here. So, so Hamilton's equations of motion, which is basically these two can be combined, is basically the Newton's law, the mass times the acceleration is the time rate of change of the momentum, which is the force. And we know that the solutions are are sinusoidal. And we know that, let's say, if the current is I naught times the sine of the resonance frequency times time plus some phase, the voltage has to be 90 degrees out of phase with that. Otherwise, energy would be created or destroyed. Right? So it's a cosine. And from dimensional analysis, the voltage has to be related to the current by something that has units of impedance. And that's called the characteristic impedance of the oscillator. And if you solve the equations of motion in order to match these up, you find out that the characteristic impedance, ZR, is square root of L over C. Okay, so you have L and C there. Those are the only two parameters that go into the physics of this model. 1 over the square root of LC is the frequency, and square root of L over C is called the characteristic impedance. It has nothing to do with dissipation because the voltages and currents are out of phase. It just has to do with, like, there's mechanical impedance. You know, do you have an oscillator of a given frequency could have an extremely stiff spring and a very large mass to get the same frequency, or it could have a soft spring and a low mass. It's just that idea. Okay? But it enters into the characteristics of the vacuum fluctuations. Do you want large electric field fluctuations in your vacuum or large magnetic field fluctuations in your vacuum? Well, that's determined by the characteristic impedance of your vacuum. Free space has a characteristic impedance, which I call Z naught. This is the permeativity of free space. This is the permeability of free space. This is you know, just this is the thing that Maxwell, when Maxwell figured out you know, the speed of light, this is the inductance. This has units of inductance per unit length, capacitance per unit length. Okay. And this is picofarad per millimeter. And this is nanohenry per millimeter, I think. Anyway, this is 377 ohms approximately. And again, there's no dissipation in free space. This is just telling you about the size of electric and magnetic fluctuations, or in a wave, what's the ratio of the electric to magnetic field? Okay. And it turns out, if you build yourself a resonator, it's very, very hard to get it to have an impedance much different than this. Typically, it's 50 to 100 ohms. So here's a transmission line. It's roughly 50 ohms. Okay. But in quantum mechanics, there's a very important object, quantum object, that has Planck's constant in it, that has units of impedance. And in my former life, as a quantum Hall many body theorist, the von Klitzing constant, which is Planck's constant over E squared, is approximately 25,812.7908 maybe ohms. Okay. And if you write down, they're connected by the fine structure constant. If you write down the fine structure constant, which remember is the fundamental dimensionless constant in QED, it tells you how strongly photons interact with electrons. It's E squared over H bar C. But that's the, okay, it's dimensionless, so it should be the same in CGS and SI, right? No. Turns out electrical units are very strange. Every time you see an E squared, you'd better put a 1 over 4 pi epsilon naught if you're going to be in SI units. So even though it's dimensionless, the actual expression, it depends on this. Okay. So this is about 1 over 137, very famous dimensionless number. And the impedance of free space is 2 alpha times the quantum of impedance. 2 because of the 4 pi h bar there. Okay. So there's a nice connection then. The quantum of impedance is very large. It's 250 times larger than the impedance of space. And that leads to engineering challenges sometimes for impedance matching and so forth. Okay, questions? Yeah.
So when it's a long parameter, it's like in the cavity, there's a single mode. So there's geometry comes into these calculated L and C.
Yes. Right.
So, but in vacuum, free space, there's no geometry.
Right. In our box, there's a geometry. I have a particular mode I'm looking at as some sign
So
form.
the dependence, but in the vacuum, the dependence on, so in the cavity, it's also mu, C naught is mu naught of epsilon based on up here. And the,
Yeah.
I guess when you take it to the vacuum, the geometry of the
Right.
L dependence gets inside the geometry.
Yeah, that's right. Right. To get the,
Get those L and C.
yeah, exactly. That's right. That's right. So if you take a wire and ask what its geometric inductance is, well, it depends on whether it's coiled or curvy or straight, but those are kind of small factors. The basic factor is it's about this much per unit length. That's going to be the inductance up to geometric factors of order unity. And if you build mu 0 times length. Yeah. And then if you make a capacitor, it depends on the area and separation of the plates. But if you have two wires separated by some distance, there's again some geometric dependence, but roughly, the capacitance of a little segment of wire to far away pieces of metal out here is about epsilon naught per unit length. Yeah. So if you make a lumped element resonator, whoop, there it was, and you just look up the total length of wire you needed to make that inductor and take into account that there's some capacitance inside the wire connecting the different strands, you'll get a resonator whose frequency corresponds to a wavelength about equal to the length of wire you use to build it, up to geometric details. Yeah. Okay. Good. So now we have to quantize our oscillator, and the method to do that is to put hats on the position and momentum and say they don't commute. And it's nice to make a dimensionless object that represents that, the creation and annihilation operators. So the flux is something I'll call the 0-point fluctuations of the flux as units of flux times this dimensionless thing, A plus A dagger, the coordinate. And the momentum is some 0-point fluctuation charge times this, right? And these guys have the standard commutation relation, and the product of these two dimensionful quantities, they're canonically conjugate, and their product is exactly h bar over 2 in order to get this commutator correct. Okay. Well, how big are these quantities? And you can go through all the algebra and everything, but there's a simple mnemonic to figure out how big those coefficients are. How big are the vacuum fluctuations? You say, well, I know in the ground state, there's some uncertainty in the coordinate and some uncertainty in the momentum. And the total energy from that should be 1/2 h bar omega. And the kinetic energy should contribute half of that and the potential half. And so you can figure out from that argument, the expectation value of the kinetic energy, the electrostatic potential energy, should be half of the 0-point energy. That gives you that the charge fluctuations are Planck's constant over twice the impedance, characteristic impedance. So now if you want big charge fluctuations, you should have a small impedance. But it's very hard to make the impedance very different from that of free space, but you can do it a little bit. If you work out how big are the flux 0-point fluctuations, it's this times ZR, characteristic impedance. And if you calculate, well, how big are these charge fluctuations on the capacitor due to quantum effects for a typical impedance of 100 ohms, it's basically 1 over the fine structure constant divided by 4 pi, take a square root. It's about 3. And it's very hard to make it much bigger or much smaller than that. So if you build a millimeter scale resonance circuit, and it's a harmonic oscillator, it's going to have an uncertainty in charge on the capacitor due to vacuum fluctuations of a few electrons, just because of the size of the fine structure constant and the impedance of free space. Depending on the details of the capacitance, you can then calculate the voltage fluctuations or the electric field inside there. And those are the vacuum fluctuations of the electric field. Similarly, you can do the same for the magnetic field. Okay? Yeah. Well, suppose suppose that I build by hand. There are similar arguments for the continuum case, but just think of this. I want to build by hand some capacitor that has no inductance and some inductor that has no capacitance. Turns out I can't do that because when the current is accelerating, there's a voltage drop from here to here. So there's electric fields also. And there's some capacitance. And the more tightly I wind the coil, the bigger the capacitance, in addition to bigger the inductance. So if I take a piece of wire straight and I make it, half a wavelength long, I can get a electromagnetic resonance in that. And if I coil it up, the resonant frequency changes a little bit, but not much. So even that inductor by itself is a resonator because it has lots of parasitic capacitance. Right. So that's why it's hard to do something different than wildly different than the impedance of free space. Unless you, instead of a wire wound inductor, you use a Josephson junction, which we'll come to. So you can put large dielectrics down. It's very hard to put large magnetic permeability. They tend to be very lossy. You can put moderately large dielectric constants like, no, that's super lossy. But you can put, silicon or sapphire and get dielectric constants of square root of 13 or something. Yeah, those have some effect. Yeah. Okay. All right. So we know that harmonic oscillators, right, have this Hamiltonian if I drop the 1/2 of 0-point energy. And the excitations, we can think of that as photon number. and the energy it takes to add a photon or to the box is a constant. It's just h bar times the resonance frequency. It's this transition frequency is the same. That's what makes the harmonic oscillator isochronous, right? You take a mass on a spring and you stretch it a lot or a little, it still comes back to its starting point in the same length of time. Something that still amazes me, even though I've been thinking about it for a long time. Well, that's great, but suppose that all I have to control my oscillator is a classical signal. I send down some voltage on a wire to drive this thing, and it's a classical voltage, whatever that means. I buy a signal generator from Agilent. It's definitely classical. Okay. Of course, there's quantum noise and fluctuations on top of that, but basically it's a classical signal that you can control. It turns out then if you try to make a single photon Fock state, I want to make n equals 1. So I start driving it at resonance and I excite to there. But unfortunately, as soon as I have a little amplitude there, it's also resonantly going up to here and here and here. And I get a special superposition of all the Fock states called a coherent state. It's sort of the closest quantum state to a classical displaced oscillator. I do not have universal control. I can only make coherent states. I can't make Schrodinger cat states, which I'll show you pictures of. I can't make states of definite photon number, etc. Okay. In order to do that, I need an anharmonic oscillator. I need something whose transition frequency here is different than here. So that when, like in an atom, so that when I drive this oscillator at this frequency, it can go up to there, but then when it tries to go here, it goes too high. It's off resonance. There's a tiny effect, but not much. And to a reasonable approximation, I can forget all the higher levels. If I don't drive it too hard, I can just go up to the first level and then back down, just like a qubit. I can Robbie flop it from 0 to 1 to 0 to 1. Okay, so in order to achieve universal control, I either need an object which is, I'm trying to control an object which is anharmonic, not isochronous, or if I want to control this guy, if I want to produce, let's say, Fock state 2, I need to couple it in some way to an auxiliary object, which is anharmonic. So that's going to be, this is going to be my microwave cavity resonator. This is going to be my synthetic atom, my superconducting qubit. And together in that hybrid system, I can achieve universal control. Okay? All right. So, so there's this paradox. We love microwave resonators. They can have lifetimes up to a second. And easily, you know, that's a heroic effort, but, you know, you can get millisecond lifetimes without working very hard, just take, you know, from the machine shop. And oscillators have a huge Hilbert space, which is great. We can do things with that. And it's just in an empty box. It's just vacuum, you know. And so that big Hilbert space could be used for error correction or to replace multiple two-level qubits, which have, you know, smaller Hilbert space. But we can't actually control this beautiful object because it's harmonic unless we have some qubit-like anharmonic thing to help us. So we can't really get rid of, we have good superconducting qubits, but they're not as long-lived as these cavities. But unfortunately, we can't control the cavity without using the qubit as a helper. Okay, so this is our cavity or circuit QED system. We're going to have some kind of resonator. We're going to have an auxiliary Transmon, it's called a Transmon qubit. We'll talk about that. To provide some anharmonicity, and there's going to be a little port here, and we're going to send in drive signals, and it's going to be able to leak back out, which is bad. It lowers the lifetime of things in here, but it's good because it gives us information about what's going on inside. Okay, questions? Yeah. Yeah. No, that's a good question. But suppose I make, it's not quite, your premise is not quite right. So suppose I make some weird shaped box and I solve Maxwell's equations in there to find the normal modes. They will not be uniformly spaced in frequency. Okay, that's what you were suggesting. That's absolutely correct. But there's what's confusing is you have modes and they have frequency, omega 1, omega 2, omega 4, and they're not uniformly spaced, but each mode can have n photons, and each of those is a harmonic oscillator with a uniformly spaced. So this is a excellent question because it's very, very common in quantum optics, even for me, to get confused between modes and excitations of modes. Yeah. So, sorry.
First quantized.
Yeah, I mean, you can find these mode frequencies by the construction I showed you of finding the Lagrangian and the Hamiltonian in a multi-mode system, and that each one is a harmonic oscillator with some frequency. But then you can excite each oscillator independently, and if you want, in second quantization if you want. Okay. All right. And there's lots of work going on learning how to control this hybrid quantum system consisting of an anharmonic object like a qubit and a harmonic object like a cavity. Okay. All right. So now we want to get to Josephson junctions. So how many of you know how Josephson junctions work? Okay, good. Not too many. All right. So the Josephson junction is sort of the transistor of superconducting qubit world. Well, I'll show you a picture of the Transmon qubit. Yeah, it's evaporated on sapphire, which is a very good dielectric with not much dielectric loss. And is about 1 millimeter in size. People your age can see it with their naked eye. I need a magnifying glass. And it's like an antenna, it's like a millimeter antenna that's going to talk to centimeter scale wavelength photons. So it's a huge atom. And the two halves of the antenna are connected by a Josephson junction. This is aluminum, by the way, superconducting. And the Josephson junction is just two pieces of aluminum superconducting separated by about a nanometer of, aluminum oxide, which is a whole loaded material science thing. It's Al2O3 minus X. It's not stoichiometric. They look horrible and ugly, but they work great. Okay. And nominally, this is a very powerful insulator, and current can't flow through there, but it's only a nanometer thick, and electrons can tunnel through that barrier. And not just electrons, but when it's superconducting, The electrons travel around in Cooper pairs of spin singlet charged 2 objects that are sort of crudely viewed as bosons. And even those pairs of objects can tunnel through this barrier coherently. So this is going to turn out to be an anharmonic oscillator. The Josephson junction is going to act like an inductor whose inductance varies with the current. And so instead of, remember the inductor had a term in the Hamiltonian phi squared over 2L. Instead, we're going to get cosine phi. And we'll explain why later, okay? So at the bottom, cosine looks like phi squared, so it's roughly a harmonic oscillator. But as you go up, it gets softer than the Hooke's law spring. And so this will be an weakly anharmonic oscillator. What are the excitations of this oscillator? It's Cooper pairs sloshing back and forth, charging this capacitor plate, negative, then positive, and this guy the other way. It's an antenna with current fluctuations in it, and therefore voltage fluctuations between these 2 capacitor plates, but it's not harmonic. Okay, so that's why it's a good qubit. And it's the anharmonicity, this is maybe 1% lower than this. Not very much, but it's enough. And we'll talk more about that. Okay, so circuit QED is, let's compare a natural atom like hydrogen, not to scale here. It's 10 to the minus 10 meters in size. This guy is orbiting 10 to the 15 times per second. Here's our superconducting oscillator. Those are the 2 plates of our thing viewed as a kind of capacitor. And the current is the electrons are, superconductors have a gap to excite break Cooper pairs, but no gap for them to coherently slosh back and forth through the circuit. And those are the excitations. And we can quantize those and get excitations of our atom. This is a millimeter in size. It's gigantic compared to this. Here's the characteristic transition frequency for this guy, 1.6 nanosecond spontaneous emission lifetime. You can define a Q of this as, anything. Even a hydrogen atom is approximately a harmonic oscillator if you only so weakly excite it so you never see the higher levels. You can't tell it's not a harmonic oscillator. So you can define a Q. It's about 4 million. The transition dipole moment, the thing that couples to the electric field, is an electron moving a Bohr radius. And that product is a debye, it's called, unit of dipole moment. This guy has a frequency of 7 gigahertz, spontaneous emission lifetime of 300 microseconds to these days even 3 milliseconds, and a Q about the same size as the natural atom of hydrogen. But the dipole moment is 30 million times bigger. And this is going to allow us to have very, very strong, we can engineer very strong coupling between our atoms and the microwave photons in the cavity and do things, I always like to say in front of audiences with atomic people, do things that atomic physicists wish they could do but can't. Okay, that's our goal. Make them jealous. Okay. So this is basically a capacitor, right? An antenna. The total charge on the capacitor is the charge of a Cooper pair of electrons, times the number of Cooper pairs that have tunneled from one side to the other, okay? And the Hamiltonian, it turns out, I will derive this later, is phenomenological Hamiltonian is the Josephson energy the tunneling energy through here times cosine of the dimensionless flux. And the dimensionless flux, if you know about superconductivity, it's the phase difference of the superconducting order parameter across the junction. We'll drive this if you're not familiar with it. The thing that's interesting is that if I were to expand this cosine to second order, I would get a constant minus phi squared, and there's a minus sign there. So it looked like an inductor. Remember, the inductor has phi squared over 2L, and this would be called the Josephson inductance. It's the kinetic energy kinetic inductance of this weak link in the wire, it turns out. So it's actually a relatively big inductance compared to geometric inductances, which are smaller because of the fine structure constant. But if I keep going in the expansion, I can get phi to the fourth, phi to the sixth. I can get nonlinearities. I can get photons to interact with each other or get an anharmonic object. Now, we're going to make that approximation, but I want to emphasize something dangerous, namely, the number of Cooper pairs that has tunneled through there is an integer. And so this phase is actually compact. When you add 2 pi to this phase, you get the same state, or equivalently, there's periodic boundary conditions between phi, the phase equals pi and minus pi. But provided you're only working down here in the low-lying levels, there's a certain regime where this quantity is large, you can expand the cosine. Okay. So this thing, what does it look like? This is an operator, which if you take away the 2e, it just has eigenvalues that are integers that can be positive, 0, or negative. The number of Cooper pairs that's tunneled could be positive or negative. What operator has the positive, 0, and negative integers as its eigenvalues? Well, that's the angular momentum operator of a rotor. And what is the cosine? That's just gravity trying to pull the rotor down here. Okay? So the Hamiltonian is exactly that of a quantum rotor. And so I can write the charging energy as something that has units of energy times the square of a dimensionless integer angular momentum operator and minus EJ and cosine of this dimensionless angle, which runs from minus pi to pi. Okay, and I can represent it as the angular momentum operator of a rotor. Okay, so why is that? Where did this all come from? I want to try to explain that. Okay, so that's like a phenomenological picture of a Josephson junction, but what's microscopic? So I don't want to do horrible many-body microscopic stuff. I just want to give you a very simple argument for why the phenomenological Hamiltonian has to be right. Yes?
Before, I thought the LC circuit was just an abstraction for the lowest mode of the cavity.
Yep.
Now, the actual capacity of the junction. So where does the junction sit in the cavity?
Good question. So right now, I'm thinking of a lumped element object, which is not representing the modes of the cavity, but representing the modes of this lumped element object, which has some capacitance between these plates. And, there's a little bit of inductance because it's a millimeter long. But this object in the middle acts like a large nonlinear inductance. So I'm really making a lumped element approximation to this object. Later, I will put it in a cavity and the cavity will also have modes. Does that help? That's a good question. I should have clarified that. Thank you. Yeah.
So before we had 5 magnetic flux in the coil,
Yeah.
now we have 5 the order of the superconductor.
Yeah. So remember that phi dot is the voltage. And I'm going to derive for you the Josephson relation, H bar phi dot, which has units of energy. That's the connection. Does that help? That's right. And it's time derivative. It is the flux up to dimensional. Yeah, exactly. But it is the flux.
It's not something you can visualize as a flux.
Well, okay. And yet, if I take cosine phi and expand it, the first term looks exactly like the inductive energy of a coil. Yeah. 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 Good. Okay. So let's go down to the microscopic level. Here's 2 pieces of aluminum separated by this insulating barrier. Okay. And electrons are waves and Cooper pairs are waves, and they can tunnel through this thing. So first we'll start with aluminum in the normal state, either because it's at 4 Kelvin or room temperature or something, warm enough, or in a high magnetic field, so that's not superconducting. And I put a voltage across here. I can think of that as raising this Fermi C up to the Fermi level up relative to this one by EV. Okay. And now the tunneling is not Pauli blocked. These states are occupied, those states are empty. Current begins to flow, and you can calculate that current with Fermi's golden rule. And the total amount of current, well, each of these guys has some matrix elements squared, and there's some density of states. Taking all of those things to be constant, the only thing that varies is how big is the voltage. And the bigger the voltage, the more electrons can tunnel. So the current should be linear in the voltage. Okay, so Ohm's law, essentially. Of course, there's this is also a capacitor, right? It's 2 pieces of metal, very close together, separated by what's supposed to be an insulator. So the electrical engineer says, oh, it's this. If I put a voltage, I charge the capacitor a little bit, but then it reaches steady state and there's some current flowing through the resistor. And this guy tells you what the conductance is or the resistance. Does that make sense? Okay. All right. Superconducting. Yes. 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 As long as you stick to frequencies such that h bar omega is much smaller than the Fermi energy, yes. Okay. Good. So you can, if you have voltage and frequency, you can get some funny things like, if the frequency is bigger than the voltage, h bar omega bigger than EV, this guy could be excited up to there with photon-assisted tunneling. There's a little bit of a story there. Yeah. Okay, so what is a superconductor? Well, it's, all kinds of fancy many-body theory. We're going to skip all that. We're just going to say, if you have an isolated piece of metal, forget about, for now, phase of order parameters, broken symmetry, blah, blah, blah. I'm just going to tell you, if I have a piece of aluminum and it contains an even number of valence electrons and equal numbers of spin up and spin down, then when you cool it down to absolute zero, there is a unique ground state where all these Cooper pairs are the electrons are bound together, and it takes a finite energy gap called 2 delta to break them apart. And then there's a continuum, because the broken Cooper pairs, the quasi-particles, can move around like in a normal metal. Okay, but there's a large, relative to the temperature, gap. Okay, now there's a gap in silicon, 0 temperature, but it's tied to a very special density, right? It's a band gap. It makes it an insulator. Superconductors don't have that property. If I add 2 more electrons to this piece of metal, it still has a unique ground state separated by a gap from the excited states. The gap is at the Fermi level, but if you move the Fermi level, there's still a gap. So that's very different than a band insulator. Okay. All right, so let's make an approximation. We got this gigantic Hilbert space, all these excited states. Forget all those. Let's just stick to one state. If you tell me the charge on this island, and assuming it's even, then I can tell you what the ground state is, and we'll just deal with that. Okay, so the whole Hilbert space we're going to deal with is labeled by one integer. How many Cooper pairs have left here, leaving a unique state, and moved over here, leaving a unique state? So if you tell me m, the number that have tunneled, I can tell you exactly what the quantum state of the system is by doing some fancy many-body calculation. But we don't need to know that. We only need to know there's a single state associated with each total charge, as long as it's even. Okay, we just saved a whole year many-body course by making that statement. Okay, so gosh, so now the Hilbert space of this combined object just lives on a lattice with positions labeled by an integer. And what does the tunneling do? The tunneling moves me to the right or the left by 1 unit. So it's just a little tight binding model in 1 dimension. I tunnel along back and forth, okay? And all of these levels are degenerate if I ignore the fact that when I tunnel a bunch of particles, I'm actually charging the capacitor. We'll put that back later. So we're going to do degenerate perturbation theory and figure out what the eigenstates of this Hamiltonian are. Is that clear? Okay, well, think of this as a position basis, but the positions are integers. And so there's like a single band tight binding model. There's some orbital on each site, only one, and you can hop to the next site. So the any eigenstate is just a superposition of all these different integer values. And you can make, instead of a position basis, you can talk about a plane wave basis, where this momentum phi lives in the first Brillouin zone between minus pi and pi. Because there's only one band. You okay with this, Matthew? Okay. All right. So remember, I told you the fact that the Cooper pairs charge, they tunnel in integer units. That means that the conjugate phase is going to be compact. Okay. So if you tell me where you are in this lattice, you've uniquely determined the state, or you can be in superposition of them to make a kind of plane wave. And that plane wave, you know, it has some velocity, group velocity. What is that? Well, if the wave is drifting to the right, there's a current flowing. Or to the left, there's a current flowing. Okay, so an object that has this Hilbert space is a quantum rotor without gravity. And the kinetic energy, angular momentum, oh, sorry. No, sorry, didn't mean to say that. This momentum, this linear momentum, actually looks like an angle because it lives in the first Brillouin zone, so it's compact. Maybe you should ignore that remark for the moment. That's just kind of confusing. Okay. Yes, right. Yeah, that's what I meant to say. Yeah. There's an interpretation of this as a plane wave with linear momentum or a rotor with angular momentum. Yeah. Yeah. So if you have a definite phase of the rotor, it's just sitting there, then you have very uncertain angular momentum. That's what I meant to say. Okay. Well, we forgot about the charging. Let's put that back. So if I tunnel a bunch of Cooper pairs, this side plate becomes positive, that side becomes negative. The total charge is the Cooper pair charge times the number of pairs that have tunneled. If I define EC, the characteristic charging energy, as the energy for moving one electron, moving a Cooper pair gives you 2 squared in the charge. So it's 4 EC times an integer squared. Well, what has eigenvalues that are m squared? That's the angular momentum operator for this rotor. Okay, so now instead of thinking about linear momentum, I want to think about a rotor, and that describes the charging energy. Okay? Yeah. Yes, yes. Yeah. So okay, so this is this is a very deep discussion. But if I have a chunk of aluminum that's a cubic meter, you know, and another one, and enormous capacitance, then it's almost degenerate perturbation theory, and it's almost spontaneously broken phase. But if you go down to really, really low temperatures, you'll find out that the phase is just sitting there having quantum fluctuations depending on what eigenstate you're in. It's not sitting there with some classical value of broken symmetry.
Well, statistically, really, it's an angular momentum.
No, if there's only charging energy, yes. But if you have tunneling, so it's a competition. The tunneling is trying to make it have definite phase 0. The charging is trying to make it have completely indefinite phase to minimize the charging energy. So that's the thing you can engineer, and that ratio determines what kind of qubit you're making: charge qubit, flux qubit, phase qubit, etc. Okay. Oh, the total charge is fixed. Yes. Right. The global superconducting phase is completely ill-defined, but the phase difference between the two pieces can be pretty well defined depending on the ratio of charging energy to Josephson energy. Good. Yeah.
like we M and N.
Yes, right. So I want to put, so if in the basis of M, this is what tunneling looks like. It changes me from M to M plus 1 or M plus 1 to M by 1 Cooper pair tunneling. In the quantum rotor picture, this is angular momentum. What changes angular momentum? A torque from gravity, the gravitational potential of cosine phi. So cosine phi suppose I have a wave function, psi of phi, like e to the I m phi, right? That's a definite charge state. If I apply e to the I phi to it, it raises m by 1. If I apply e to the minus I phi, it lowers m by 1. So that torque is changing the momentum by exactly plus or minus 1 unit. So it beautifully represents tunneling. Okay, and that's why in the phase picture, the Josephson energy is some number minus EJ times cosine phi. It represents tunneling. Now, the microscopic calculation of how big that tunneling energy is, that just gets buried and somebody tells you what that number is. Okay? That's right. So if this was the entire Hamiltonian, the eigenstates would have definite phi. Yes, these two have exactly, this is the Hamiltonian in the charge basis, this is in the phase basis, but they have the same spectrum. Q. Yeah. Oh, wave vector Q. Yeah. The name of our wave vector though is phi. Yeah, that's right. But we have both hopping and charging. And so the full Hamiltonian has 4 EC n squared. So it's 4 EC n hat squared, and n hat is minus I, ED phi, it's conjugate to that phi. And so you get, you have to solve, now you have to do work, solve, unless you're into, what are those, the solution has a name, it's some standard function, which is now escaping my brain. But basically you have to do it on at least I have to do it on a computer. Yes, Matthew equation, thank you. Matthew equation. Okay, so I'll try now, may not quite get this part finished, but now we've quantized our synthetic atom in this cosine potential. And when you solve the Schrodinger equation with this term minus EA cosine phi, you find discrete energy levels and they're not uniformly spaced. At first, the anharmonicity is negative. Once it gets very highly excited, it's just the rotor's whirling around and forgets about gravity, and then the energy goes like m squared. But at first, it has a small negative anharmonicity here. So this is slightly close. This is 7 gigahertz. This is 6.9 gigahertz, something like that. Okay, so now we want to put that object, which remember physically is this little Transmon qubit, a millimeter in size. I want to put that inside a box and have it talk to the harmonic oscillator mode, which is the photons in the box. Okay, so there's the box or half of it. There's the piece of sapphire. And there's a dipole coupling, sort of the position of our oscillator. If I kind of expand this, forget about the fact that the phase is compact, but just expand this as a kind of and cosine as a kind of phi squared and phi to the fourth. This is the and I can if I manage, if this transition frequency is close to the resonance frequency of the cavity, and this one is not, then I can approximate my qubit as a two-level system described by Pauli matrices, and sigma x flips me from ground to excited or excited to ground. And then I multiply by the electric field in the cavity, and that's the dipole transition matrix element in the Hamiltonian. So an excitation in the atom can turn into a photon can turn into an excitation in this synthetic atom. And the size of that coupling is easily 100 megahertz. And I remember the first time I calculated that in 2003. Took me a long time to get all the factors of volume to cancel out and the units right. And I couldn't believe it was so huge. So it should be easy to see. It was a very exciting day. So the size of that coupling is the transition dipole moment times the 0-point fluctuations of the electric field in the cavity. And it's 100 megahertz when you divide by Planck's constant.
Where does the electric field leak out of the cavity?
Well, for now, let's just say it's a closed cavity, and I just have an electric field, from some mode, and the antinode of that electric field is right here talking to the qubit. Yeah, and then remember the 0-point fluctuations, the root mean square electric field due to vacuum fluctuations turns out to be the thing that gives you the matrix element that converts an atom excitation into a photon excitation. Okay, so I think I will stop here just summarizing. I'll go into this more tomorrow. I'm going to pick out one mode of the big microwave resonator with number of photons A dagger A and resonance frequency R. I'm going to pick out two states of my anharmonic oscillator, the qubit, and has transition frequency omega q, and sigma z tells me whether I'm in the ground state or the excited state. And then there's a dipole coupling, and then there's some damping, like maybe there's a hole in the cavity to let signals in and out. Maybe there's some junk on the sapphire that, or in the Josephson junction that eats up energy. That's all in here. This is called the Rabi Hamiltonian. If this frequency is close to that frequency, the qubit and resonator are close, you can drop the rapidly rotating terms from this by making what's called the rotating wave approximation, and consider that when you de-excite the resonator, you must excite the atom to approximately conserve energy, throwing away the things where you de-excite the cavity and de-excite the qubit. They're there, but they're not so important. And then there'll be a further approximation I'll talk about tomorrow. If you detune the qubit frequency from the cavity frequency, then when the atom tries to fluoresce into the cavity, it's got the wrong frequency. So the photon jumps back. But there is in second order non-degenerate perturbation theory a leftover effect, which is this dispersive coupling. And it tells us that the frequency of the cavity depends on the state of the qubit, and the frequency of the qubit depends on the state of the cavity. And that's where we get all the quantum control and measurement capabilities that we can do. These terms commute with the state of the qubit and the state of the cavity. So I can use the cavity to make a QND measurement, quantum non-demolition measurement of the qubit, and I can use the qubit to make a quantum non-demolition measurement of the number of photons in the cavity. So that's what we'll talk about next time. Thank you. Questions? By saying that my qubit or my atom only has two states. Sorry? Because the transition frequency in hydrogen corresponds to 3/4 of a Rydberg, so it's a far ultraviolet photon. And I can't make mirrors for it. I can't control, I don't have lasers that work very well at those frequencies. Right, and here I can make this coupling G is enormously bigger than I can do with natural atoms. And it's so large that even the second order effects, this term is G squared over some detuning. Even that second order effect is so huge that this coupling here is much bigger than any damping term. And that never happens in optical cavity QED. Well, you can get them, with heroic efforts, you can make them maybe approximately equal, but we can make it 3,000 times bigger. That's where we win. Somebody else had their hand.
So based on from James Francis's first limit, they are in some sense approximated in the strong limit. Well, but in the real experiment, you are thinking of the controls based on this approximated. Is this sometimes harmful?
Yeah, so for pedagogical purposes, I'll make these approximations. When we actually simulate the experiments, we have to do numerics because the qubit is not that anharmonic. The cavity detuning is maybe not, big enough or small enough. So we usually do everything numerically, but you can understand what's going on qualitatively by making these approximations. Yeah. What are the main sources of noise? So the things that cause decoherence and dephasing, this is something of a mystery. We know that the transmon is sitting on this piece of sapphire. There are very large electric fields in the vicinity of the Josephson junction because it's such a large effective inductor. And those electric fields go into the insulator between the two pieces of aluminum, which is some junky, not very good oxide. And the surface of the sapphire is great, but the surface, Wolfgang Pauli said that God invented the bulk, but the devil invented the surface. So there's junk on the surface, things called two-level systems, which we don't know what they are, but they absorb energy. There's a whole, now material scientists are now beginning to help us figure these things out, but we really don't fully understand. But how did you clean the surface? When you use the lithography and you put some resist down to pattern things, did you leave some junk behind? There's all kinds of mysteries, which it's a black art. So nobody really has a good understanding of the Hamiltonian of the dirt.
The beginning you treated the Transmon, the oscillator with the linearity.
Yep. Yeah. Quantitatively, you can go wrong there. And when we do the calculations on the computer, we actually keep lots of levels of the Transmon, recognizing that it's only weakly anharmonic. But there are, and in fact, to calculate this thing, it's much better to start with the weakly anharmonic oscillator and estimate this because it's proportional to the anharmonicity, rather than making the two-level approximation and then doing perturbation theory there. There's a whole story behind that, but basically, you have to do everything. If you want to be quantitatively right, you have to keep the bigger Hilbert space and do everything numerically. But that story's, this is a very good approximation, but calculating that number, it has to be done very carefully. There are corrections beyond the simple perturbation theory. Yeah.
On the hand, you want underlaying
Yeah.
But on the other hand, you're not, that.
Yeah.
So,
There is only one well because it's compact.
well, on the other hand, like when it starts leaking out, like way. Transition. You think of, on the other hand, we think of dissipative state of the current bias, running down.
Right.
Washboard.
Yes. So, yeah. So that's, okay. So the reason that it's compact is, I can view this as a capacitor with some sort of object. I think it's drawn like that to represent the Josephson effect. That the only way for charge to get from this plate of the capacitor to there is through the Josephson tunneling mechanism. But if I hook this up to, a current supply or something, and maybe an inductor, then it's not compact. Why is that? Because the phase across here, call this phase 0, can change continuously through the inductor. You can just follow the order parameter and it can change by 17 pi, depending on how much current is flowing. Then it's non-compact. Here, but this guy, here, if I turn off the Josephson effect, the charge is a good quantum number. Here, if I turn off the Josephson effect, it's still going through the inductor. So the charge is not well defined. That's the difference. Now you mentioned dissipation. So in this picture, yeah, you can apply a current bias, and then you can end up with a cosine plus something linear in phi. And you can get running downhill and that gives voltage and so forth. Here, you cannot current biases without hooking something up to it, and we didn't do that.
When you hook up to it, that's when you make it non-compact.
Yes, yes. Okay. Thank you.